Okay, welcome to topic 4, organic and biological chemistry. In this topic, we're going to have a look at organic molecules and biological functions. So, bit of an overview here. Organic compounds are hydrogen-carbon compounds. They'll also have some other elements, so they might have oxygen, nitrogen, phosphorus, and possibly some halogens. And in this case, we're looking at up to 8 carbons in the main chain, but also branching side chains and potentially some rings, so things like benzene. So organic compounds have two main features. They've got the hydrocarbon chain, which is non-polar. It can be either in a chain or a ring, and it's unreactive if it's saturated, so it means it has no double or triple bonds. It can also have one or more functional groups, so it could have a hydroxyl group or an amine group. We're going to have a look at these groups as we go through. And these functional groups, they're the things that take place in the reactions. But they also influence physical properties, so boiling points due to the polar or the polarity of that site or how many polar sites there are. The molecular formula is when we talk about the number of hydrogens, carbons, and we represent it so, C4H8 is the molecular formula. This means that the molecule contains 4 carbons and 8 hydrogens. I've got some molecules here for you to have a go at. See how you go writing the molecular formula for each of these molecules. So pause the video and see if you can get these. Okay, so the first one, C7H8O2. So let's actually count these up. So at each of these joins we have a carbon. So we've got the 6 in the ring. And then we've got the one down here making 7. Now each carbon has to have 4 bonds. So if we have a look here, we've got 1 going out to that oxygen, 2, 3, and 4. So that's got 4 bonds. Let's have a look at this carbon, 1, 2, 3. So it needs another one out here, and that will make the hydrogen. Let's have a look at this one here. So we've got 1, 2, 3. So that needs one attached to the hydrogen. This one's got 4. This one needs another one. And this one needs another one. Now we can count that up. So we've got 3, 4, 5, 6, 7, 8. That's where our 8 hydrogens come from. And then our 2 oxygens. Have a go at the remainder. So you should have got C7H9N. And here for molecule 9, you should have got C4H7O2. And for molecule 10, you should have got C6H10. The empirical formula is similar to the molecular formula, except that it expresses it in its simplest ratio. So for the example C4H8, we can divide both of these by 4 and we can end up with CH2. Now this is not the number of carbons and hydrogens in the molecule, but it is the ratio of carbons to hydrogens. So if we go back to our molecules here, the only one where we can actually pull out a common factor is molecule 10, and we could pull out a common factor of 2, so we could make it C3H5 as our ratio. Okay, structural formula shows us how things are arranged, because if we had the molecular formula of C4H8, we could have some different structural formulas but have the same number of molecules, same number of atoms. So we could have a simple butane with our H8, but we could also have a structural isomer of this, so we could have this arrangement instead. Okay, so some other terminology we need to know. So structural formula we've seen before. So in a structural formula of this molecule, we would have the C, and then we would draw out each of the bonds. So our structural formula is about drawing out each of the bonds. You can see here in the condensed structural formula, what we have is the CH3, CH2, 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 and C. So the bond is drawn for the non-hydrogen carbon bonds, but then back to the CH. So anything that's not a carbon and hydrogen bond, we will draw the bonding for. Now this could be condensed further. So this is one version of condensed structural formula, but we could condense it further by putting the CH2s in brackets. So we've got 1, 2, 3 of these, so we could put CH2, 3 of those, and then the bond occurs at the next one, so we couldn't do it there, and then a H at the end. So we could condense that further. So basically what we're trying to do is abbreviate where these bonds are, and we know that CH3, well, that's going to be this sort of branching. And because we're writing out actually quite large molecules, we end up trying to abbreviate them in terms of sticks and lines. So we could do a zigzag shape where we have our double bond O on the end. So where each of these points are is where we have a carbon bond. Right, we also need to know about structural isomers. So isomers are the same molecule, but they've got a different arrangement in space. So if we have a look at these two versions of propanol, we can see that they're both propanol. They've both got the longest chain of 3 hydrocarbons. They've both got an alcohol group. But we can see that one propanol has the alcohol group at the end, whereas 2-propanol has the alcohol group on the second carbon. But we need to be able to say, well, yeah, they're both propanol, but they're isomers of each other. Similarly, we've got these two molecules here. One of these is a ketone and one of these is an aldehyde. But they've both got the same molecular formula.